I did send out an email yesterday, but the smart evaluations just went live. So I think this year especially, it's important for us to get feedback from you because sort of we've gone through this big change, obviously, in the middle of the course. And I think like everyone else, we're hoping that this is not something that drags on into the fall. But in case it does, having, lots of good feedback from students about how they found this experience will be helpful for us if we have to do this in the fall again, right? So we sort of made this change on the fly. And I think in heat, I hope you feel the same way. I think we've done a reasonably good job. But any kind of feedback from you about things that you liked or things that you didn't like would really be beneficial for us moving forward. So I appreciate that more than 10% of the students in the class have already filled out this smart evaluations. But if you do have the chance to do it, we would really appreciate it. Particularly maybe the written comments about sort of this transition. There's also on the My Courses webpage, there is a discussion board. I've set it up to be anonymous, so you don't have to put your name to anything. But we're trying to collect feedback there too. If you want more immediate feedback for us, because we won't see any of these things on the smart evaluations until the class is over. So again, thank you for taking the time to do that. I really do appreciate it. So like in the other Thursday lectures, what we'll be doing today is going over some problems. So we've been talking about heat exchangers. So we'll do some heat exchanger problems today. We did one problem on Tuesday. So we're going to try to do 3 today. And the first, I don't think is on the handout for the heat exchanger problems, but I wanted to show you a case where we're going to use the log mean temperature difference method. So in this particular question, it asks us to think about a cooling process where we have some fluid where we're given the specific heat, and we're cooling that from 80 degrees to 50 degrees Celsius, and it tells us the mass flow rate. It's in a counterflow, or we'll see parallel flow heat exchanger, and we're trying to decide which configuration would be better for our application. The cooling fluid, we're told, comes in at 15 degrees Celsius, and we're told the mass flow rate of the cooling fluid. So then the problem asks us, what is the required transfer surface area? So how much heat transfer area do we need for the heat exchanger in both different configurations? So we'll compare sort of a parallel flow and a counterflow heat exchanger. And then we're told that the convection coefficient of the process fluid side is 3,500 watts per meter squared Kelvin and 4,500 watts per meter squared Kelvin, respectively. So if we draw out the problem, here in my sketch, I'm only showing the parallel flow, but for the counterflow case, it's just the flow in the tube will be moving in the other direction. So we're given some information about the hot fluid at the inlet and the outlet, and we're told the inlet temperature and the mass flow rate of the cold fluid. But we don't know the outlet temperature of the cold fluid. We're told the heat transfer coefficient on both sides of our tube, so inside the tube and outside of the tube, and we're asked to find the area for heat transfer required in parallel flow and in counterflow. So if you think about the area, that's going to be the perimeter of our cylinder multiplied by the length. So as the area goes up, assuming the diameter of the tube stays the same, then what we end up doing is making a longer and longer heat exchanger. So you could see that could be a limitation if you want to fit your heat exchanger in a particular, piece of packaging. So the assumptions that we'll make for this problem, first we'll assume that the system is at steady state. We're going to do that for all of these heat exchanger problems. We're going to assume that the fluid and material properties are constant. We assume that basically for every question that we do in this class. We'll assume that there's no losses to the surroundings, right? So our heat exchanger is adiabatic, so that all of the heat that comes out of the hot side goes into the cold side and none of it is lost to the atmosphere. We're going to assume that there's no axial conduction along the tube, even though there may be a temperature difference. So basically we're assuming that this heat transfer is small. And we're going to assume that the wall of the tube is thin and that there's no fouling on either the inside or the outside of the tube. So we talked about this in the lecture, but we'll need to find sort of the effective heat transfer coefficient, or the net resistance between the hot fluid and the cold fluid. So when we do this, we're going to assume that there is no conduction resistance in the tube, and that there's no sort of gunk on the inside or outside of the tube, which would add resistance to the problem. So I talked about this in the problem that we did on Tuesday as well. But for these heat exchanger problems, I always like to have kind of a nice methodology that I can use for any type of problem, right? So in this case, we've got these heat exchangers, and I'm going to use this 2x2 matrix for every heat exchanger problem that I do. So first, I want to see what's the objective. So am I trying to find how big my heat exchanger is supposed to be, or am I trying to find how much heat is being transferred? And in this case, we're asked what the heat exchange area is, right? So if we're asking for that area, that means we're looking at the sizing. So next, I have to choose the method. So there's the log mean temperature difference and the effectiveness NTU method. So there's two different options here. So for log mean temperature difference, we need to know all of the temperatures at all the inlets and the outlets. And it's really best if we use it for parallel and counterflow heat exchangers. Personally, I think anytime you get to a more complicated geometry than that, effectiveness NTU is a good way to go. But in this case, I actually added this problem just to show you the log mean temperature difference. So we're going to pick the log mean temperature difference. So we're trying to do sizing for using the log mean temperature difference method. Sort of the nice thing about the log mean temperature difference, though, is that we're going to use the same equation whether or not we're sizing or trying to find the heat. It's not really a different process. So here we might remember from thermodynamics or from our lecture on Tuesday that all of the heat that comes out of the hot side of our heat exchanger goes into the cold side. So if we assume that there's no phase change in the fluid, then we can say that the heat on either side is going to be m dot times the specific heat times the change in temperature. So we know that the magnitude of these things is going to be the same on both sides. So I've made both of these terms positive by taking the hotter temperature minus the colder temperature in both of these brackets. In heat transfer, we talk about this fluid heat capacity rate, or capital C, and that capital C is going to be m dot times Cp. So we can write this same equation like this. We also know we're going to use the log mean temperature difference method. So I'm going to start with a parallel configuration. So here I have equations for the heat transfer, which looks like Newton's law of cooling, but instead of multiplying by delta T, we multiply by the log mean temperature difference. And now I have an equation for the log mean temperature difference where I have delta T1 minus delta T2 divided by the natural log of delta T1 divided by delta T2. So here the difference between the parallel and the counterflow geometries is going to be how we define delta T1 and delta T2. In both cases, delta T1 involves the hot inlet fluid. And then delta T1 is going to be the hot inlet fluid minus the cold fluid that touches the hot inlet. So in this case, because it's a parallel flow, the hot inlet is in communication with the cold inlet. So then down here, we have the hot inlet minus the cold inlet. Delta T2 always touches the hot outlet, and in this case, the hot outlet is in communication with the cold outlet. So we have T hot out minus T cold out down there. In a counterflow heat exchanger, we really use the same equations, except our delta T definitions change. Delta T1 is still the hot inlet, but if we look in our counterflow example, our hot inlet is in communication with the cold outlet. So we have T hot in minus T cold out. And our hot outlet over here is in communication with our cold inlet. So we have T hot out minus T cold in. So these are the equations we're going to use, and we'll use this equation for Q to find the area. So I need to find the heat transfer some way, and then I can isolate the top equation here for area and calculate how big my heat exchanger is supposed to be. So first, we'll start finding the heat. So in this case, we know that all the heat coming out of the hot side is the same as all the heat going into the cold side. So the nice thing is I know everything on the hot side. So here I know the inlet temperature, the mass flow rate, and I know the outlet temperature. And from conservation of mass, I know that the mass flow rate must be the same. I'm also told the specific heat of the hot fluid. So I can put all that information into my calculator. And I can find the magnitude of the heat that's transferred from the hot fluid to the cold fluid. So here, the hot fluid is losing 210,000 watts or 210 kilowatts, which means that the cold side must be accepting all of that heat. So now I can look at the cold side to try to figure out the cold side outlet temperature. So I'm going to use now my same equation for heat, but now I'm saying that the hot side heat is equal to the cold side heat if I look at the magnitudes. And I can isolate this equation for the cold outlet temperature. So here I know the cold inlet temperature, I know the heat transfer, I know the mass flow rate on the cold side, but I don't yet know the specific heat on the cold side. So that wasn't given to me in the problem. So now I'm going to have to look something up on a table. So I'm going to have to find some material properties. So in this case, I look at table 8.6, which tells me about properties for saturated water. This is just like we saw this last week too, where I don't actually know what my average temperature here is. So I'm just going to guess. And I'm going to guess here that my average temperature is 300 Kelvin, which is the same as assuming that the outlet temperature is 39 degrees Celsius. So I picked 300 because it's a line on my table. I mean, you could really pick anything here. We'll check it at the end. So here, if my outlet temperature is 39 degrees Celsius, then I have a specific heat value. You can see here too, if you look in this column, the specific heat of the liquid is not a very strong function of temperature. So it's probably not going to matter too much what our temperature assumption here is. It's also important to remember that because here we're talking about the liquid, we have to pick from the table CP, F. So the F tells us that it's the saturated liquid, whereas G would tell us it's the saturated vapor. So now we know our specific heat, or at least we have an assumption for our specific heat. I can put that into my equation for my outlet temperature on the cold side. I put some numbers into my calculator, and I find that the outlet temperature is 35 degrees Celsius. Now, I assumed that the outlet temperature was 39 degrees Celsius. So really my assumption's not perfect. So here I'm high 4, so it would actually be, I think, 298 degrees Celsius. But I'm not going to interpolate, and we saw that that specific heat was a very weak function of temperature. If you're on an exam, even if you pick what you feel like is a specific heat that's off, just kind of make a note and say that if I had time, I would go through and iterate this and find a better value for a specific heat, but I'm going to just carry on as if this is correct. So now that we know all of our temperatures, we can start to go and use this equation. So now we know our delta T1. This is for the parallel flow heat exchanger. So I know my hot outlet and my cold inlet. So the difference there is 65 degrees. I know my delta T2 is 15 degrees. So I can take those two numbers and put them in and find my log mean temperature difference, which is 34.1 degrees. So that's good. Now I know almost everything in my equation for Q. So here I just sort of carried over the fact that I know my log mean temperature difference. I have this equation for Q, but Q is not what I want. What I actually want is the area. So I isolate this equation for the area. And I know Q. I know the log mean temperature difference, but I don't yet know the effective heat transfer coefficient. So here we come back to the fact that we're going to assume that we have a thin wall for our heat exchanger, so that the resistance from that wall is not important. So if that's true and there's no fouling on the tube, then I can get my effective heat transfer coefficient using this equation. So in this problem, they told us the heat transfer coefficient on the inside of the tube and the heat transfer coefficient on the outside of the tube. So I don't have to do any kind of internal convection analysis. I put this in and I can find my effective heat transfer coefficient. Once I know my effective heat transfer coefficient, now I know everything in this equation. So I can put some things into my calculator, check my units, and I find that the area is 3.13 meters squared. And that's good because that's what the problem asked me to find. So now I know how to find the area. So I did this for the parallel flow heat exchanger. And now we're basically going to do the same process for the counterflow heat exchanger. So the good thing is, we're not going to, so when we got the outlet temperature for the cold side, we were just using the first law. So the first law doesn't care about how big our heat exchanger is. It's just telling us if I lost this much heat from the hot side, then I must have gained all that heat on the cold side, provided my heat exchanger is insulated. So my temperatures are not going to change. But my delta T's are going to change because the equations are different. So in the counterflow heat exchanger, the hot inlet touches the cold outlet, and the hot outlet touches the cold inlet. So these temperature differences are different. So here, my delta T1 is 45 degrees Celsius, and my delta T2 is 35 degrees Celsius. So these two numbers are closer together. And then my log mean temperature difference is 39.8 degrees Celsius, which is higher. So I think it was, I want to say it was like 35 or something, I think, in the parallel flow case. So here, what happens when you set it up in counterflow is, like we see in this picture here, the temperature difference along the length of the heat exchanger stays more constant, right? So let's see how that affects the area. So here we're going to use the same equation that we did in the parallel flow. It's just our log mean temperature difference is different. We still have the same heat transfer coefficients on the inside and the outside of the tube. We have our new log mean temperature difference. We put that information into our equation, and here we see that our counterflow area is 2.68 meters squared. So just by changing the plumbing on our device, so by taking the tubes and connecting them to different ports, we've reduced the area or the size of our heat exchanger by 14%. So this is a pretty powerful thing. If you're sort of in an industrial setting and you're using this kind of a heat exchanger, setting it up in counterflow usually will give you sort of a more efficient result. So you're selling a smaller device here, right? Which means that you can reduce the price and sell it to more customers, or you can keep the price the same and increase your profit margin. This message is from Evelyn, and she really loves Baby Shark, so she colored this for us. So does anyone have questions either in the chat or audibly if you want to unmute your mic? Does anybody have questions about how we did this example? Okay, we will move on to the next problem. Let's do this one next. I think this is the next one on the sheet. So in this problem, we're given a shell and tube heat exchanger. Now, this is not just a parallel flow or a counterflow heat exchanger. It's one where the shell comes in, or the tube comes in, right? And it snakes back and forth along through the shell. So the tube is making several passes inside the shell. And they tell us that there's multiple tubes inside this shell. So there's this one big bath of fluid on the outside and a lot of little tubes that are running back and forth to try to transfer as much heat as we can. So we're told some information about the cold inlet. We know the temperature is 15 degrees Celsius, and we know the mass flow rate is 2.5 kilograms per second. And we're told the outlet temperature on the cold side. So it's always nice when we know at least one side. If we know everything on one side, then we know we can find the heat transfer. So here on the hot side, we're told the inlet temperature, but we don't know the mass flow rate. And then on the outlet on the hot side, we're told the temperature, but we don't know the mass flow rate. So here, maybe you're looking at this and you're already thinking, I can use a first law analysis here on the whole heat exchanger, and I can see that all the heat that gets accepted on the cold side must have come from the hot side. So I could do that to find the mass flow rate of the hot oil. We're told our heat transfer coefficient on the hot side. We know that we have 10 tubes, and each tube makes 8 passes. So a pass is once down the shell. So right? So to get back to where we started from is 2 passes, right? And we're told the diameter of the tube. What we're asked to find here is the length. Now, I took this to mean, and it's not really explicit, so this would be, we'd want to be more explicit on an exam problem. But I took this to mean the length of each pass. So you could find different lengths. You could find the total length of all the tubes put together. But I guess no matter which L you're finding, you would still have shown that you knew how to do the heat transfer part if we get to there. But the L that I'm taking is the L that I'm showing on my diagram here. So the length of one pass. So assumptions, we're going to assume that the problem is at steady state, that the fluid and material properties are constant, that there's no losses to the surroundings, and that the tube is thin-walled with no fouling. I guess we're also assuming here that the heat transfer in here, if I just go back, I don't think I wrote this on my assumptions list, but we're also assuming that the heat transfer here on the ends where the tube is turning around, that's negligible compared to the rest of the heat transfer. So we're only talking about the length of the pass. We're not talking about how much height there is as it's turning around there. So we're also going to assume that the flow is fully developed in the tube. I think it tells us that in the problem, but we're going to check that numerically anyway. So again, for all of these heat transfer problems, when we're dealing with heat exchangers, I want to come back to this 2x2 matrix right at the beginning, so that when I first look at the exam and I say, like, what am I supposed to do? Then hopefully if I go back to this sort of 2x2 matrix, then I can sort of help myself start the problem. And I think once we build up that inertia, things become a little easier. So here they're asking us for the length of the tubes, which tells us something about the size, right? So ultimately the length will tell us what the heat transfer area is. And because we have a fairly complicated geometry, we're going to deal with the effectiveness NTU method. So we're going to try to use this process here, so I have kind of a flow chart for how to do these problems. First, I want to pick the geometry. Then I want to find my big C values. Then I'll find effectiveness using the definition. And I'll use the value for effectiveness to find NTU for using one of the correlations in the textbook. And then I'll use NTU to find A because the definition of NTU has an A in it. So first we want to pick the geometry. So here we can see from this picture that we have a shell and tube heat exchanger. So there's tubes running through this shell. We have one shell pass. So what that means is that there's no baffles in the problem. If we have baffles, then we would have like lines running vertically here, so that flow here would have to kind of go up and down across the tubes multiple times. So that would be shell passes. But here we don't have any of those because there's no baffles inside of our problem. We have an even number of tube passes at 8. So now I'm going to look at table 11.4 because I want to get an expression for NTU as a function of effectiveness. So here I look and I see that there's some shell and tube heat exchanger correlations, right? So now we have one shell pass and an even number of tube passes. So here we can use this equation. Now it's actually a set of equations because I think they wanted to make the equation look a little bit cleaner. So we have this value of capital E, but everything here is a function of effectiveness and CR, big CR, so the ratio of my big C's. So here I have an equation for NTU as a function of CR and effectiveness because E is a function of effectiveness. So now I would like to try to use that equation, so I need to find my Cmin and Cmax values. So here we need to know the CP of water and oil, and we need to know the mass flow rate on the hot side because we don't have any of that information yet. So if I look at these equations, if I did an accounting here, it's nice that I know the mass flow rate on the cold side, but that's the only thing that I know. So we look for water specific, or first I guess we're going to look at engine oil. So we need average temperature. So we're going to say that the oil temperature is 130 degrees, so that our average temperature is 403 Kelvin. So now I'm going to assume that's about 400 degrees Kelvin. So, I mean, again, we can pick off pretty much anything from this list, and CP is, again, sort of a weak function of temperature here. So we get a value for CP from the table. Again, you got to watch the units when you're doing this because it gives us CP on the table in kilojoules per kilogram Kelvin. But I'm going to change that right into joules because I want to change this into watts later. But if you kept it as kilojoules, that would be fine. You just really got to track your units when you're doing your equations. So now I know CP of oil. I don't know the M dot of the oil yet. So I can go to the water side and try to find my temperatures, right? So here I know my average water temperature is 50 degrees Celsius, which is 323 degrees Kelvin. I'm going to say that's about 325 degrees Kelvin, and I'll pick that information off the table. So far, it looks like I only need specific heat. But I noticed in the question, they never told me what the heat transfer coefficient in the tubes was. So I'm going to have to do some internal convection analysis here. So from the table, and I think I might have chopped the table off a little bit here, but I pulled off all of the values that I would use to do an internal convection analysis. So the specific heat, the density, the viscosity, the fluid conductivity, and the Prandtl number. So that we would have had to remember from last week. But again, if you didn't do this now, as you went through the problem, you would sort of come to a point where you say, oh, I need to know H. I got to go back to that table. So if I do this, now I know enough information to find my big C on the cold side, and that's just over 10,000 watts per degree Kelvin. So now I need to find the mass flow rate on the hot side. And like we said when we introduced the problem, I can get this from doing a first law analysis on my whole heat exchanger. So I don't know the heat transfer, but I can find the heat transfer if I look on the cold side because I know everything about the cold side now. So here I can find my actual heat by looking at values on the cold side, and I can see that this is just about 190,000 watts. I know that all the heat that gets accepted on my cold side has to have been lost by my hot side. So now if I take the same value of heat, I can find stuff on the hot side because the only thing here I don't know is my mass flow rate on my hot side. When I do a problem like this, I like to set my problem up as, so here I'm trying to find the hot mass flow rate. So I multiply this by the cold mass flow rate, multiply by the ratio of specific heats, multiply by a ratio of temperature differences. I like to do this because then I worry less about the units. So if my CPs are both in the same unit, then it's fine and the units will drop out. And if my delta T is in the same unit, again, the units are fine and they drop out. So when I do this, I see that the mass flow rate on the hot side is 5.2 kilograms per second. So now I know the mass flow rate of the hot oil, which is one of the things I think the problem asked me to find. So now I can go back over here from when I looked up the specific heat on the hot side. I can calculate my big C on my hot side, which is 12,152 watts per degree Kelvin. So now I know my C hot and my C cold. So C hot is 12,000 watts per Kelvin about, and C cold is about 10,000 watts per Kelvin. So I know that my C max, big C max, is on the hot side, and big C min is on the cold side. So I can find my ratio of big C's. I always want this to be less than 1, so C min is on the top, and it's 0.86. So this is nice because now it took us a while, but we found all our values of big C, and now we can find our effectiveness. So I'm going to find effectiveness here from the definition. So in this effectiveness NTU method, depending on which flowchart you're using, you might have to find effectiveness first, and you might have to find NTU first. Whichever one comes first on the flowchart, you find that from the definition. So here we're going to use effectiveness to find NTU, but we need to know the effectiveness first. So our effectiveness is Q actual divided by Q max. I know the definition for Q max is going to be big C min times the biggest temperature difference I can find in my heat exchanger, which is going to be T hot in minus T cold in. I have a numerical value for the heat transfer, but I kind of want to show you how to set this up. So I could define the effectiveness, the actual heat transfer, by the heat transfer on the cold side or the heat transfer on the hot side. The reason I like to do this is, again, because units are going to drop out. So here, because my big C on the cold side is my C min, then C min is equal to C cold. So I can just cancel those out, and my effectiveness is going to be a ratio of these temperature differences. And because my temperature differences are in the same unit, then it all drops away. So I get my effectiveness is 0.483. You could have done this by just putting Q actual on the top and putting more information into your calculator. But like I said, I'm good at screwing things up on my calculator. So this way I think it's a little bit safer. So now I have my effectiveness, which is good because I need my effectiveness to find my NTU value. So we already found the equation that we want to use for NTU. And it's a bit of a bear because here we have a bit of an ugly equation. So first we're going to have to find capital E, which is a function of effectiveness and CR. And then we'll put that into NTU, which is a function of CR and capital E. So there's two things I'm going to find here. I've separated them on the page. First, I'll find capital E. So I know all of this information. I put it in my calculator, and I find that capital E is 1.73. I put that into my equation for NTU, and I find that the answer is 1. So now I know how many NTU that I have, right? And now I'm going to try to use my definition of NTU to find the amount of area that I need in my heat exchanger to get the performance that I want. So I remember that the definition of NTU is equal to the effective heat transfer coefficient multiplied by the heat transfer area divided by C min. Ultimately, what I want to find here is the length of a tube pass, but that's going to be a function of the area. So here I'm going to take NTU and isolate for area. I know C min and I know NTU, but I don't know the effective heat transfer coefficient yet. So here I want to use the same equation I used in the last problem, where my effective heat transfer coefficient is what's shown here. I guess I just don't like to say it out loud because it's a bit of a mouthful, right? But I want the reciprocal of the sum of the reciprocals, I guess. So I know the heat transfer coefficient on the hot side, but not the cold side. So here, my cold side fluid is running through the tubes, so I have to do an internal convection analysis through the tubes. Now the problem tells me to assume that it's fully developed, because these tubes are probably going to be pretty long, so that's probably reasonable to assume that it's fully developed the whole way, but we'll check that out too. So based on the information that I pulled off the table, I'll use this definition for Reynolds number. I know the mass flow rate on the cold side, I know the diameter of the tubes, and I know the viscosity. So I can put that in, and I see that it's turbulent flow, so that it becomes fully developed after 10 diameters. So again, we're going to assume that this pipe, which is snaking back and forth along our shell, is longer than 10 diameters. So we're going to assume that it's much longer than that, so it's fully developed probably for the whole width, or pretty close. So if that's true, then I can use this Nusselt number correlation. And if you're forgetting how to do this, we can always go back to the information from last week, so the videos from problems last week, and we would have done a problem like this much more in depth. But here I can pull a turbulent flow correlation. I'm going to find my Reynolds number, and I know my Prandtl number because I looked that up off the table, and I can see that my Nusselt number is just about 120. I remember that the definition of Nusselt number is the heat transfer coefficient multiplied by the diameter of the tube divided by the thermal conductivity of the fluid. So I looked up the thermal conductivity of the fluid as well. But if I didn't remember to do that, if I didn't sort of have the foresight to see I was going to have to do this, then I could just look that up now. And if I do that, I can find a heat transfer coefficient on the cold side, which is nice. I already know the heat transfer coefficient on the hot side, so I can put this information into this equation, and I can find that my effective heat transfer coefficient is 354 watts per meter squared Kelvin. So now I have the information that I need to calculate the area of my tubes. So I can put this in. Again, we're going to check through our units, and we find that we need almost 30 square meters of tubes, right? And we know that I think there's 10 of these tubes, right? So there's kind of a bundle of tubes, and then each one snakes through 8 times. So if I look at the problem, I know that the total area is going to be the number of tubes times the perimeter of each tube, which is pi times d, times 8 lengths. So again, I guess it's important to realize that I'm neglecting what's going on when these tubes are turning around. So then I can rearrange this equation for L, and I know the area, I know the number of tubes times the number of passes, so that's 80, and then I know that we have pi times d here, and d is known. So again, if you were doing this on a test, I defined L, which wasn't very well defined in the problem, but I defined L as the length of a tube pass. If you would have said the total length of all the tubes, then you would just be 80 times higher than this. So I get the length of each pass is about 4.7 meters. So it's pretty big, right? And I don't know, maybe some of you have been on some co-ops where you have seen some pretty enormous heat exchangers. So, you know, maybe you think of this as being big, or maybe you think of it as being small, depending on what your experience has been. So this is what the problem asked us for. So now we're finished with the problem. All right, so we can celebrate. Does anybody have questions about this problem? All right, I will close down this window. So this is our last heat exchanger problem. And here we have truck coolant is cooled by air in a cross-flow heat exchanger where both fluids are unmixed. So I know the terminology here can be a little bit tricky. Unmixed means that my flow is separated into different channels or different tubes. So here we have one flow going through our tubes labeled as fluid A in this picture, right? So it's all separated into tubes, and the flow in those tubes, they can't mix with the flow in the other tubes, so it's unmixed. Now fluid B here is running over these tubes, but the way we would imagine it is that there's fins or plates that are connecting, holding all these tubes together. So maybe they're all brazed in together in these sort of, separated by these fins, so that the fluid, once it passes into the heat exchanger, can't come over these fins. So the airflow or the flow in fluid B also can't mix with the flow in the other channels. So fluid A is separated into tubes, and fluid B is separated into channels. So both of these flows are unmixed. It tells us that atmospheric air enters at 30 degrees Celsius with a particular mass flow rate, and water enters with another mass flow rate at 75 degrees Celsius. And it tells us the diameter of the tubes. It tells us the overall heat transfer coefficient, which is always nice. That means that we won't have to do any kind of internal convection analysis, and the total heat transfer area. So now it asks us, what's the temperature of the water? So this one's a little different than the last one we did, because here we know the size, we just don't know how much heat is being transferred. So we know the temperature on the hot side inlet and the mass flow rate. We know the mass flow rate and the temperature of the cold inlet, but we don't know either outlet temperature. So this is one of the times where, even for complicated geometries, you can use the log mean temperature difference. You just have to look it up on some kind of like ugly table and try to graphically read it. So I think effectiveness NTU is a good idea for these complicated geometries. But here, because we don't know either outlet temperature, we would not be able to use the log mean temperature difference, even if we were willing to look up on a chart or something. So we're told some things about the heat exchanger, like the effective heat transfer coefficient and the area, and we're asked to find the hot outlet temperature. But once we knew that, like, we could ask this question to also find the cold outlet temperature or the amount of heat that's being transferred. So we'll assume the problem is at steady state, that the fluid and material properties are constant, that there's no losses to the surroundings, and that the fluid is unmixed on both sides. So again, we want to go back to this 2x2 matrix. So our objective in this case is to find the amount of heat transfer. So because we didn't know the outlet temperatures on either side, there's no way for us to quickly find how much heat is being transferred, because we don't know what's going on the hot side or the cold side. And because I don't know any of the outlet temperatures, or I don't know delta T on either side, I have to use the effectiveness NTU method. But I would choose to use it in this case anyway, because we're not just dealing with a counterflow or parallel flow heat exchanger. So here, I know the process that I'm going to use, so I have a flow chart. I want to pick the geometry, find my big C values, find the NTU from the definition, use an expression or correlation to find effectiveness, calculate Qmax, and then with Qmax and effectiveness, calculate the actual amount of heat transfer. So first we'll try to pick the geometry. So we know that we have a cross-flow heat exchanger, and it's unmixed on the hot side and unmixed on the cold side. So because it's unmixed on both sides, then I go to my table here, 11.3. I look at cross-flow with single passes, so none of these flows are doubling back and pushing back around. And we have the flow is unmixed on both sides. So I have one expression here that gives me effectiveness as a function of NTU and CR. So this is what that expression looks like. So I got to find CR. To find CR, I do the next thing on my flowchart, which is how do I find all my values of big C? So for big C, we need to know values of specific heat for both fluids. But in order to find the specific heat to get the best estimate, we would need to know the average temperature on the hot side and the average temperature on the cold side. But because we don't know the outlet temperatures on either side, we'll have to estimate for both. So first, for the air, I'm going to look. So I know that it has to be between 300 degrees and 350 degrees Kelvin. So here, if we look at CP, is a very weak function, right? So I would be fine on a test if you picked 1,007 or 1,009. I just know it has to be somewhere in between there, so I picked 1,008 joules per kilogram Kelvin. So then I put this into my problem, and I can find big C on the cold side. We'll do the same thing on the hot side. So here, again, I know it's coming in at 348 degrees Kelvin, and I know it has to cool down, right? So I'm going to say it cools down to about 300 Kelvin. So I'm going to assume that my temperature is 325 degrees Kelvin. So here, when I pull this off, I get 4181. I guess I picked something a little lower than this, or maybe I just wrote down the number wrong. But again, you can see that the specific heat of the fluid is not a big function of the temperature. So I'm just going to pick a number here. I put that in, and I find big C on the hot side. So now I want to compare these two things. So I know that the big C on the hot side is 5 times less than the big C on the cold side. So C min is on the hot side, and C max is on the cold side. I take the ratio, where the ratio is always less than 1, and I find that it's about 20% or 0.2. So now I can try to find NTU. So I know my definition for NTU is going to be my effective heat transfer coefficient multiplied by the area divided by C min. So I already know what C min is. The problem was nice to me because it told me what the effective heat transfer coefficient was, and I know the area. So here I can see that my NTU is just about 0.5. Now that I know NTU, I can go back to my equation for effectiveness, which is a function of NTU and CR, and I've done some work to find both of those things, so now I can plug them back into this equation. So here I have this equation. I know CR and I know NTU, so I can put those numbers into my calculator. Again, I like to simplify as I go along because I don't trust myself to just put it all into my calculator at once. And I see my effectiveness is 0.37. So it's good that I know effectiveness, but the reason that I want to know the effectiveness is that effectiveness is going to be Q actual over Q max. So if I knew Q max, then I can find Q actual. So the next thing on my list is to find Q max. So Q max is always going to be C min, so the fluid whose temperature moves more easily, multiplied by the biggest possible temperature difference we can see in the heat exchanger. I know all this information, and I can find that Q max is 4.8 kilowatts. Almost 4.9 kilowatts, I guess. So now that I know Q max, I can use the definition of effectiveness over here and the fact that I know the effectiveness to find Q actual. So I can rearrange the expression for effectiveness to find Q actual. I multiply these things together, and I find the amount of heat that's transferred in my heat exchanger. So that's good because I'm going to use this information to find out what I need to know. But in this case, you could think about it. Your client asked you, I think they wanted to know what the hot outlet temperature was. Right? So what we actually want is T hot out. But now I know how much heat is being transferred. So then I can say big C on the hot side multiplied by delta T on the hot side. I can isolate this equation for T hot out, put some numbers into my calculator, and get an expression or get the value of the hot outlet temperature. If I wanted to do this on the cold side, I could do that as well. But honestly, I'm not sure if we did that in the slides. But it would basically be the same process, just we would have Q actual be big C cold times delta T on the cold side. But this is all the problem asked us for. So I can convert this back to Celsius, and I see that it's 58.3 degrees. So here we could go back and we assumed an average temperature for T hot. And it's not that far off. You can always increase your accuracy if you want to iterate. We could go back and do this whole thing and keep doing it on a loop until the T hot average that we find was equal to the T hot average that we assumed. But honestly, the specific heat is a pretty weak function of temperature, so I wouldn't spend time doing that. Unless, if your application required a very accurate answer, then you'd have to do that. We can find the T cold on the outlet side doing the same process. So here we took the same equation, but now we're isolating for cold on the outlet. We get a value, and we can check this approximation as well. And that's, even though the problem didn't ask us for the cold outlet, going through this step of checking it helped us check our assumption that we made. So, if you were doing this in an application that required high accuracy, you probably would want to figure this out. But here it's not that far from the assumption that we made. And again, the specific heat's not a very strong function of temperature. So if you needed that much accuracy, you would probably want to go through and also not assume that the wall of the pipe was thin. So this is, I guess, our last message from Gabrielle here. You want more jokes? One more jokes? Well, even if you didn't, here it is. See, I guess it runs in the family. I'm going to tell you the bad jokes, even if they're... So a word I know has 6 letters. It contains 1 letter. What? So I think it has 6 letters, and if you take 1 letter away, you get 12. I guess the first hint is this picture of eggs. And the answer is dozens. So if you take 1 answer away from dozens, you get a dozen, which is 12. I know you were on the edge of your seat, right? So that's our last example for heat exchangers, and really our last formal example in the course. So does anyone have any questions about how we did this problem or how we do any problems for heat exchangers? Okay, well, I think with that, I will let you go. Next Tuesday, I think what I'm going to do, although I'm open to suggestions if people want to either chime in now or write me an email or use the discussion post, I think what I'm going to do is a review of the entire course next Tuesday. And then in the department, maybe you've had to write midterm exams, but we're starting to get feedback on how the first rounds of midterms went virtually. So I think that's helping us inform what we want to do on the final. So next week, we will give you what our process is going to be for the final exam. So I think we have something. We're just finalizing it now. So does anybody have any questions about the course in general? Or baking tips? All right. Well, thank you for coming. And I will see you all, I guess, on Tuesday. Thanks very much. Yes, the final will be cumulative. We will review everything in the class. I guess when you think about the method, so there's no way for a heat exchanger or a heat transfer problem to not be like the first module, because the first module is just sort of general heat transfer stuff. So we'll probably, I would expect that you would want to know how to do conduction and transient conduction. And I would expect that you would want to know how to do internal, external flows for heat, to find H, and that you'd want to know how to do heat exchangers as well. But you could be given a problem just where you're asked to find some kind of resistance network, which is essentially what we did in Module 1. So my plan for next week is to review everything. So I have we'll see how far we get. I think it's like 70 slides. So we'll see if it spills into the Thursday, then we'll have to live with that too. But if anybody has any other suggestions, feel free to chime in now or to send me a communication versus in some other avenue.
Can I ask, what are we doing?
Thank you, everyone.
Next couple weeks, we still have a couple. Just have a quick question.
Shoot.
What are we doing for like the next couple weeks?
Sorry, it's hard for me to hear. I don't know if the volume is low. I'm trying to turn the volume up on my computer here.
Yeah. Sorry, just wondering, what are we doing for like the next couple weeks? 'Cause we still have a couple weeks left of classes.
Yeah, so ultimately, I think that it's a little bit in flux. Typically, what we would do is next week would be the third case study, and then the final week would be review. So we're going to pull the review up by a week.
Okay.
I think, although I'm not sure yet, I think the final Thursday, we want to do the multiple choice part of the exam at a different time than the scheduled exam time, so that you have enough time to
Oh, really?
to sort of write the final and then upload it. So we may split the exam up,
Okay.
and if we do that, one of our options for where we put the multiple choice exam would be the final Thursday class. But that decision hasn't been made.
Okay. Fair enough. That could actually be quite useful because I found that, especially right now, exams are kind of piling on top of each other at the same day.
Yep.
You know, it just kind of happens that way. Like I've got 2 tomorrow, 2 next Friday, you know. So it'd be helpful to spread things out for sure.
Yeah, and I think so. Part of our thought was, so we're spreading things out, but we're also because I think that everyone will need more time than they would traditionally have on an exam, because you're asked also to sort of prepare the exam materials either by printing them or maybe you're reading them off a screen. But then also when you're done your work, you have to somehow submit that, right? So maybe on Camp Scanner or something, and all that takes time.
We're doing a system dynamics test tomorrow where they're having us. It's not multiple choice at all. They're having us just submit our answers during the time window, and then you get like more time to upload the solutions afterwards. So I can let you know how that goes if you want.
Yeah, so that's one of the things. So I would definitely appreciate your feedback on that. I had heard in our faculty meeting on Wednesday that people were doing that, and I kind of like that idea too, so that hopefully that decreases the amount of stress that everybody feels while they're uploading their documents. And in case there's some sort of technical issues, then yeah. So I think that there are some
courses can cut out on you too, so
Yep.
you just got to prepare for that.
Yeah, so we would definitely appreciate any feedback that students have of exams that they've taken already. We're trying to get feedback.
Well, I took physics, and they were really nice and gave us just like a 6-hour window to do it, which was more than enough time for that any of us needed. Which, you know, it worked fine, but I almost feel like it was too generous. But I'll take it.
Yeah. So then it's interesting. So did they extend that based on when people have accommodations for longer time? So if you had time and a half, would that 6-hour window turn into a 9-hour window?
I don't know.
Yeah.
I mean, I think it was mainly because of time zones as well. I
Yep.
mean, physics are always night exams, so they just made the window like 3 to 9 instead of like 6:30 to 8:30 or 6:30 to 9 or whatever it was.
Yeah, so that's definitely an issue too. I mean, we're lucky our exams, I think, at 4:00. So I think that's not terrible for time zones. But I mean, certainly I don't want anybody waking up at like 3 a.m. to have to write their heat exam, you know.
Yeah, no, that's why they're having us do the systems exam at 12 instead of some people having to do it at 8.
Yep. Yeah, it definitely makes sense.
Makes sense.
So we'll start sharing our plans next week, and then hopefully we can, end on some kind of process that will work for everyone. I mean, that's certainly the goal.
Yeah, awesome. Thank you.
You're welcome. All right. If there's no more questions, thanks, everyone.